Okay, well, today's the big day, deadline for the code generator for the big project. So we'll answer questions, whatever the questions there are, and then move on. So, how's it going?
Good.
Good.
Oh, good.
Says half the class.
I forgot it was due then.
Really? You finished that?
We did on Tuesday.
Do we have any questions?
Do you have any questions? Does anybody have any questions?
We did direct code.
We did direct code and that was a lot simpler.
As long as that's
Switch?
okay. No.
Oh, direct code technique to do all the checks for,
For the code generation.
so you said if it's this instruction, then it's this number that you, and then else if it's
We
this
did
instruction, do
like
the,
case. If it's
or,
a-
yeah, case switch, yeah. Yeah, that's good, that's all right.
And then we just
Yeah, we switched on the mnemonic. And then.
Yeah, the mnemonic, which is an enumerate. You did a switch on the mnemonic, which is an enumerated, which is a good thing to switch on. Enumerateds and switches go together, like a horse and a carriage.
And then ours is like each line is a new line. So each first line.
Yeah, and then so your code, you have one instruction per line of the code, the object code. Wow, it sounds like everybody's doing really good. Gee, maybe there's no,
Wait, why do we have to do this?
We had a question about, I think we might have answered it.
Well,
Oh,
there. This was kind of interesting.
because we were in the beginning, we had
Oh, no.
separate string formats, but then we put them all in one to output them, because you have to return it right away. But you can't do string dot print, because it doesn't format them like the format does. Because there another way to print it out other than just returning it?
I guess I don't understand your question. You used string,
We returned a string dot.
you return a string, and you can return a string using that formatting convention. I mean, the easy way to format that is to use that formatting capabilities of the,
The string dot format.
string dot format.
Okay. But you couldn't do like string dot printf.
Well, I think it's, you have to do that, you have to print it out eventually with system.out.print,
Okay.
right? So, I mean, where you decide to do that
Okay.
is up to you, but I think the thing to do is to get it,
To have it as a string. And then
yeah, to have it as a string, and then once you get the whole thing done, then, the generate code returns a string, right? And then you just print that out. Okay. So we don't have, so here's the translator thing, slide that shows the, so basically what you are implementing this time was the translate method. Is that right?
Yeah.
All right, well, gee willikers. I was going to title this slide Code Generation. I mean, not this slide. I was going to title this lecture Code Generation, and because usually we have to spend a whole, on the day that it's due, but maybe everything is all,
So to test it, we just need to copy and paste.
yeah, make sure it runs.
Pepe.
Yeah.
Okay. I love Pepe because you just put it in source, you click build, and it does the object code, and you check if it matches, and if it matches, you're golden.
Oh, that's great. That's what you can do. I didn't even think about that. Yeah, you can check the PEP8. That's kind of like your unit test. Yeah,
So
you can see exactly if the code matches.
So then you don't have to worry about making a program that actually is logically correct.
Oh, right. Yeah. Because you're not. Yeah. You're not testing. You don't have to test the execution of the program.
Although you kind of can sometimes. We did it once, and it kind of worked.
On accident.
You can actually write a meaningful program in this subset of PEP8 that you're writing the assembler for.
From the Pepe help menu.
Oh, but then there were features. No, because now you should think about this. Maybe this assignment is getting so easy, I mean, so routine now that I should start requiring you to have a symbol table.
Well,
Can you imagine what it would be like to do a symbol table?
this part was a lot easier than the last part. The last part took a lot of time.
Well, even this part took Ashley and I working on it together 2 hours to do.
That's not long at all.
Like 2, so if we're working together.
Not 2 hours.
Probably 2.5-ish. We did more testing stuff than actually the writing. of it.
Yeah, well, it's true that because everything was all, I mean, because you basically had the main program all set up and everything, as all you had to do is just plug in those little
Right.
methods in there. And once you see how to do it, it's pretty straightforward.
And there was just the dot commands, the empty, and the non-empty instruction were really the only 3 generate codes we had to do, right? And then we checked.
Non-unary, unary, and
Oh yeah, sorry. Empty, non-unary, unary, and dot command.
Okay, well, good deal.
And empty was nothing.
Any tips that you want to give to the other people for posterity?
use the formatting.
Use
That was helpful.
string F. Is that what it's called?
No, it's the string dot format.
String dot format, yeah, that uses the same formatting conventions as the printf.
So when you're putting out bytes, you make sure you have 2.
Yeah, so you know how to make sure you have. Is there a way to? How do you do that with it?
You figured that out.
Yeah.
That was really nice.
Yeah, how do you figure? How do
You
you
do percent like 0
0,
to x. So it means you have 2 zeros.
choose
Or 2 places.
2 places? Yeah,
Yeah, that was really nice.
yeah, yeah. That's why. Yeah, you know, I used to not. When I discovered that capability in Java, I immediately said, "Oh, this is the way to do the. This is the way to do it," because you know the PEP8 assembler and simulator is not written in Java. That's written in C++ with the Qt development environment, and they have a very similar. Of course, we just take advantage of their library as much as we can. In fact, actually, it's a little interesting if you're interested in how it's done. They have a regular expression facility. Now, those of you who are in automata theory, you know what regular expressions are, right? They are equivalent to what?
Oh shoot.
What are regular expressions equivalent
An
to?
FSM.
Yes, a finite state machine. They are equivalent to finite state machines. So the lexical analyzer, we don't even do a finite state machine for the lexical analyzer in the PEP8 in the PEP8 app. Instead, we write regular expressions, and then that engine, you know, behind that is a finite state machine, you know. But the regular expression, it's a lot easier just to write the regular expression for the tokens.
We have.
And then we didn't have to do a finite state machine, but we do a finite state machine for the parser.
I wonder if there's a better way to do this, so we don't write the exact same code 10 times. So we have our abstract operand spec dot generate listing, and we have mod 256 and divided by 256, and we do that in every case for the switch under the non-unary instruction.
Oh yeah.
Is there a way to do
Yeah,
that?
that's a good question. The problem is you're doing 2 different. You can't have a function return 2 things. Is the problem. Excuse me.
We could make another function and have it grab from that function, and then they'd just be in one spot. But I don't know.
But is that really more efficient?
Yeah, I mean, you're just calling it, it's a one-liner.
Save.
It's a one-liner. I mean, you know, having sometimes having one-line functions is good, as opposed to having the line in the code.
But this is more easy to follow, I guess.
By the
See what
way,
you're printing out.
By the way, we're talking about, this is an interesting point, because we've talked about optimizing compilers before. You know, one way that a compiler can optimize, you understand that when you call a function, you have to push stuff onto the runtime stack, and it switches over to here, and then you got to do the return. Don't you agree that instead of actually doing that, if you had the code for the function right there in the calling function, that it would be run faster? That's called inlining. Some compilers will actually do that. You will write a function and they will inline it. You see what I mean? So instead of doing the function call, they'll actually put the code for the function right in line.
The compiler does that?
The compiler can do that.
That's cool. So instead of using
That-
a symbol, it just puts it right there?
It puts all that code of the function just right in there, and then it's faster because you don't have to call you have to do the runtime stack and do the call and blah, blah, blah. So there's always overhead in calling a function. So if the function is short, an optimizing compiler can actually inline the function.
Wow.
I feel like if we started doing pointers now, we probably are going to start doing pointers now, but they're going to make a whole lot more sense now than they did before.
Oh, you mean actually understanding how pointers work? Yeah, that's what we're going to do. And as a matter of fact, that's a great segue.
Okay, I guess if we don't do code stuff now, we can do this, and then we have more time to review for the final.
That's right, we would.
I think that's probably the best way to do it. Because like you said, otherwise you have to make a function.
We tested it
Pretty thoroughly?
right?
We
Yeah.
hope
Tested
so.
it pretty thoroughly?
That's what I thought last time, and then I put a space somehow.
And then
Are you going to be,
got,
It must have been when you turn on a computer and you press spacebar. Because I tested it so many times.
would you tell us how you're going to test it?
no. Well, I mean, last time I had that big suite, so,
You can use the same big suite? So
no, well, I mean, I don't know if I used the same big
We might
suite or
have.
not.
We might have
We
gone
might
back to our
have hand-typed
homeworks
the whole
and...
thing in.
No, I don't, on this one, it's up to you to generate your own testing strategies. That's part of the
I guess
things that you should think hard about.
I probably can't ask
So
about
instead-
caching right now, huh?
No, yeah, cache is for next time, yeah, you're right. Okay, well then, if there's no more questions about code generation, let's move on to our array, how arrays are handled. Okay, now, watch this. Now, in C++, do you remember this rule? In C++, how do you indicate call by value in the formal parameter list?
90%?
No, I said call by value.
In the formal...
In the formal parameter list, how do you indicate call by, trick question
Isn't it
actually.
just like you don't do
Yeah, a trick question. You just say like, int n or something like that. You don't, so by default, it's called by value, okay? Then in the formal parameter list, how do you indicate call by reference?
the ampersand.
That's with the ampersand. Are you with me? Okay, but there's this rule in C++ that says if you pass a parameter and you don't put the ampersand, how are you calling it?
By reference.
No.
Oh, yeah.
Now you should know this. So we have a call by reference and a no.
By value.
If you're putting what in it?
Yeah.
If you put nothing, if you pass an array, so here, let's do this example. So, an array.
It's an array, then it's called by reference.
Yeah.
And so that if you put an ampersand, it's constant reference.
No, you don't put an ampersand.
Okay, never mind. You're right.
An array is always called by reference?
Okay, the default, okay, so what we're saying is that if you pass an array and you don't put an ampersand, it is still called by reference.
Right.
That's a rule of C++. So what we're saying then is that the default of,
An array.
the default for like an int or a double or something like that, if you don't put an ampersand, it's called by value. If you do put an ampersand, it's called by reference.
Right.
But, so the default is called by value. It's different for an array. In an array, the default is called by reference. Okay, so now that you should really know. That you really, 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 really should know that.
Okay. If there is an ampersand, does it change anything, or is that just not valid?
Well, see, that's a good question. Now, I wonder what would happen if you put an ampersand in the array. If you pass an array and you put the ampersand. I wonder if you'd get that's probably legal.
But it
Wouldn't
would
it
still
not
be
be-
called.
But it would change what the array, Yeah, I can't think, I'll find I can't think of when that, if I've ever seen that done before.
Would it be an error?
I know what we have done before, and which is common every once in a while, is kind of the same kind of thing. It's when you pass a pointer by reference, which means that the pointer can change.
Right.
So it would be kind of similar to that, but I can't think in my mind, I can't think of an example in all my programming where I've ever done that. Whereas I can think of times when we've passed parameters by reference. Actually, I think we did that in the data structures course before.
This is the thing, I think we did that before.
Yeah.
Didn't we do it on that one program where you're asking me?
Which one?
Okay.
Rotate.
Now, okay, so now here's the situation, you guys. Suppose we have over here a global. So suppose this is vector sub 0, vector sub 1, sub 2, sub 3, sub 4, and sub 5, right? And we pass, and we have, and we have this vector, let's just say it's global. And then suppose that we up here, suppose we have something like the runtime stack, and we have a bunch of things here on the runtime stack, ... And let's suppose that then that the stack pointer is here. Okay, and here is vector. Well, here, let's do it like this. And we have passed vector. All right? So the question is, what's going to be the value of vector? Because vector is going to be on the runtime stack. Are you with me? So with this picture, supposing these are integers, so each one of these is 2 bytes, what will we say for vector? Vector will be dot what? If vector is a local variable, or a parameter rather, if vector is a parameter and it's been pushed onto the runtime stack and it's here, and if each one of these is 2 bytes, what will vector equate?
Dot equate.
Yeah, dot equate.
4.
Yes, this will be dot equate 4. And why will it be dot equate 4? It's because from here down to here, the offset is 4, right?
Assuming those are integers.
Yes, assuming these are integers, 2 bytes. Yeah. So the offset equals 4. And that's why vector will equate to 4. But now what will vector be? What will the value of vector be here?
The address.
It'll be the address of what?
The first.
Of the first byte of vector over here. Are you with me? So let's just make up a number. Let's just say that this number is 002A, which means that over here, this would be 002A. Are you with me? So this would be the address of this. Right? Now, you guys, suppose we, somewhere in this code, suppose we say, actually, you know what? This wouldn't have, just to keep things, to make sure that our naming is not confusing, let's call this vect. Because vect would be which variable, which would be the actual and which would be the formal. This would be vect. Vect would be the formal parameter and vector would be the actual parameter. Okay, so is everybody clear on that? Okay, so this would be vect equate for blah blah blah. And suppose down here somewhere we say vect sub 3 gets 5. Over here. So, are you with me? Suppose we say vect sub 3 gets 5. So now, what over here, what gets 5? Over here, what should get 5 is the 5 has to go here. That's what we are saying, because by convention, all arrays are called by the defaults. All arrays are called by reference. So you see, we don't have when we pass the array, we don't want to have to copy the array onto the stack. By the way, that's why in C it's like that. It's very rare that you have a situation where you want to make a whole copy of the whole array on the runtime stack when you call it. That's extremely rare. Actually, I can think of one example where that needed to be done. And the algorithm was very, very simple if the entire array had been copied onto the stack.
Didn't we do that on when we had to draw them at the beginning of the semester?
Oh, no, that's when they were local.
Oh.
If an array is local, it is on the runtime stack.
Okay.
Are you with me? Mm-hmm. But when you pass it, it's never on the stack when you pass it.
Okay.
But if it's local, it is on the stack. And that's common. That can be quite common. But there was one, there's a really slick recursive algorithm that prints out all the permutations. And it turns out to be a really slick implementation if you can do call by all the values of the array were copied onto the runtime stack, so you had your own local copy to work with. And in those programming languages where you didn't have this default being called by reference, it's really slick. It's really nice code. But otherwise, what you have to do is, in order for that algorithm to work, you have to have it a local copy on the runtime stack and actually copy the values so that they'll be there on the runtime stack so that you can permute the values. Anyway, I digressed. Now let's think about this. Let's think about this problem. How on earth are we going to do vect sub 3 gets 5? Well, what do we have? Obviously, what are we going to have to do? We're going to have to take this 3 and put it in the what?
Index register.
Put it in the index register. Then, because 3, you have to
the number of bytes.
Multiply it 5 times, and that's going to be, so you multiply 3 times 2, and that's going to be 6. Is that right? Okay, sorry for the technical difficulties here, but I'm going to have to be dubbing the lecture from now on because we have lost our audio. So here we're discussing the situation where we have an array that is a global array starting at address 002A, and the question is, how do we do the statement vect sub 3 gets 5? So first thing we have to do is, so this is the way the compiler would translate it. First thing we have to do, the compiler has to generate is load accumulator 5 immediate. Okay, so that gets the 5 in the accumulator. But now the question is, how do we get that into vect sub 3? So we load the index register with 3 immediate, and then we arithmetic shift left the index register because there's 2 bytes per cell. Okay. And then the question is, how do we store what's in the accumulator? How do we get that actually into the array, into vect sub 3? Well, what we do is vect is, now what is the value of vect? The vect is the offset, right? So that's 4, right? And then what we need here is an addressing mode. What does our addressing mode need to do to get that 5 into vect sub 3 way over there in that global array? How does it do it? What does it have to do? Well, let's look over here. remember the value of vect is 4. That equates to 4, right? So what do we have to do with that 4? What do we have to do with that 4 that vect is? What we have to do is we have to take the stack pointer and add that 4 to it, right? So 4 is the operand specifier, and what we have to do is add the stack pointer to it. So here, SP plus the operand specifier, right? Okay, now what is that quantity, SP plus operand specifier? What is that quantity? That's the address of where the 002A is, right? That's that address. That is an address. And if we look over here, okay, so it's mem sub that SP plus operand specifier. Now what is that? That is 002A, which is the address of the first byte of vector, right? So what do we have to add to that? We have to add that, the index register, to that. Yeah, are you with me? And then once you add the index register, that's adding, what was it, 6? Or wait. And then it's mem that is actually where it goes. Sorry for this audio problem, but I hope this is not too difficult for you here. And so guess what, you guys? Here is the Sxf addressing mode. It does exactly what we need, and the reason it is an addressing mode is so that we can do exactly this. It's mem of SP plus operand specifier, and then plus X outside that extra little bracket. Okay, so that's what it does. So the way we do that store is, here is our new addressing mode, Sxf. All right. Okay, I sure wish I knew what I was saying here in the original lecture, but that's the way it is. All right. Okay. So now what let's do is let's do an actual example. So here is a program that we're going to translate. I don't see exactly which figure this is because I'm dubbing this before I composing the video, and so sorry for the rough edges here. But anyway, this is a program that we're going to translate. I think that's what's going to be what we're showing. All right. And here's some more yakking about the global variable. Oh yes, I remember what happened at this point in the lecture. The example that we're going to do is not an example with a global array. It's going to be an example with a local array. So the question is, how are we going to get the address of the first byte of the array, pass that as a parameter? And so the concept is going to be very similar to this, but instead of having it be a global array, it's going to be a local array. And so because it's a local array and the default is called by reference, we're going to use that MOVSPA, that MOVSPA instruction. Okay, so here's the program that we're going to translate. And the first thing we should do is take a look at the Runtime Stack for this program. And I'm saying something here, scratching my face. And I don't remember exactly what I was saying during the lecture. This is all done in my office later with this dubbing and whatever. Okay, so I'm glad you're working with me on this. Okay, so here's the program we're going to translate. And after I get through doing this dubbing, then I'll splice these slides in here. And sorry this is a little ragged, but frankly, I don't want to have to re-record the video on this, so you're just having to put up with my dubbing here. All right. Okay, so blah, blah, blah. I'm saying something about the slide there. And the slide is going to be showing up on your screen there, but I haven't set the slides up yet for this video production, and so I'm not sure exactly what I'm talking about. Eventually, we'll be writing some code on the board. And, okay, stalling here for time a little bit. Come on, Warford, let's get with the actual program. Man, is this what you guys have to put up with? Going so slow? Let's get a move on here, Warford. Okay, here we go. Oh, we're about to get something on the board here. All right. So first, branch to main. Okay, so let's go over here. Let's do main over here on the sideboard. All right. Now, when we branch to main, we'll put a little documentation here. Okay, I notice that you guys aren't too keen on documenting your little comment there to set off the new main program section. So first thing we better do is draw the runtime stack for main. Okay, so the first local variable is that array, and it has 8 cells in it, right? So there's the 8 cells of the local variable, and the local variable is named vector. It's all spelled out. Vector sub 0, 1, 2, 3, 4, 5, 6, and 7. So vector sub 7 is the last one. Yeah, and then the next local variable is what? I think there was what is it? N or num. What is that? Num items, something like that. Okay, so and then that's all the locals. So this is our stack frame. Has all those items on it. Okay, and then whenever we are up here in main, we have to declare what vector and num items are. So the stack pointer will be pointing to the top of the stack there. That's going to be, there's the SP, and that's, so the offset for num items is what? What's the offset for num items? That's 0, right? Because the stack pointer will be pointing right to num items. So we'll have num items dot equate to 0, and then we'll have the vector dot equate to what? 2, I think. Yep, 2. Okay, because that's the offset from the stack pointer, or the first byte in vector in this local. Okay, and now here we have, is this main? Right, main and sub SP. But now, how much sub SP do we have to do? We have to allocate the whole thing, right? Is that right? Too bad we can't get the chatter from the audience here. And that's 18 altogether, right? Because it's 16 for the array and 2 for the local variable. But now what about the trace tags? What is that num items? What kind of value does it have? It's an integer, right? So that'll be a #2d. And how do we do the trace tags for an array? #2d 8a, 2-byte decimal 8-cell array. And then when we sub SP 18. immediate, but now how do we do the trace tags on this sub SP? The first one is, you got to do these in order, the right order. So the first one is vector, and then the second one is the num items. Okay, so there's the trace tags for that. By the way, somebody asked me if you're going to have to do the trace, if you're going to have to put the trace tags in on the final exam, and I said no. So I'm not too concerned about trace tags. But for the homeworks, you have to have the trace tags. Okay, so that's a requirement for the homeworks, but I won't bother with that, grading that for the exam. All right, now what's the first thing that happens? We've got a for loop, I think. Right? I think it's a for loop. Oh, no, it's not a for loop. The first one is to input the value into num items. And so num items is a local, right? So how do we input? So that value right there is going to be an integer. Yeah? Okay. Well, at least I don't have captions here. And then making some kind of a point there. All right, let's get moving here. Warford, what's the big holdup? No, talking some more. Students are asking more questions, and because we can't hear the audio, we've lost all this audio. Okay, some more messing around here. Making some kind of point on the code, and I don't remember what. All right. Anybody here know how to read lips? I can't tell what I'm saying. Anyway. Oh, yes. What we have to do is we have to get the... We're making the call. We're making the call to the first function, which is a void function, so there's no retval, right? But then the parameter is v. The formal parameter is v, and because it's an array, it's called by reference. And then the second parameter is n, which corresponds to num items, and that's also called by reference. Then above that, we will have the ret address, the return address, and then we'll have j, which is a local variable in the method. I forget what the method's called. I think it's getVect or something like that. Okay, so first thing we've got to do, how do we get this? How do we get the address of the first byte of the array? So look, here's vector. How do we get the address of that vector into v? That's what we have to get. So we move SPA. We move the stack pointer to the accumulator. So the stack pointer is the address of the top of the stack, and then we add accumulator. Well, you know, I remember somebody made the comment, you don't need to do this because you're just adding 0 to it. But this, for documentation, we're going to say add accumulator. Oh no, sorry. Yeah, that was the next one. We have to add accumulator vector immediate, because what is vector? Vector equates to 2. So we add 2, that offset. So now the accumulator has the address of the first byte of vector, and then we store accumulator -2 stack relative. So here's vector, right? The first byte of vector. So if we were to write the address in front of vector, you know, if we were to write that address there, that address is what's going into the cell that's labeled V at location -2 relative to the stack. All right? Now, how do we push the second parameter? Okay, so we have move SPA again, because it's also called by reference, right? And this time we do add accumulator num items. And here's where a student said, wait a minute, you don't need to do that because you're just adding 0. Yeah, you're just adding 0, but this is good self-documentation, right? Just to show that we're pushing the address of num items onto the stack. And then store accumulator -4s, because you see n is 4. So if that x is the address of num items, then that address x is going up to n. And now we sub sp for immediate to allocate the storage, and we need to put our trace tags there. So what are we allocating there? First we're allocating first we're allocating v, then we're allocating n. Then we call getVect, and then when we return from the call, we'll add sp for immediate, and we'll deallocate. You're supposed to deallocate these in the opposite order, pound n and pound v, etc. Now we're running a little short on time, so we'll let you finish that out. The call to the other function is similar. It's quite similar. And now what we have to do is we have to look at the code for the function getVect. So let's go. The first thing we have to do for getVect is we have to take a look at the stack frame for getVect. So after we call that, during the execution of it, the stack pointer will be at the top of that stack frame. And so what variables do we have there? We have v, n, and j. V and n are the parameters, and all of these are offsets, right? So v dot equates to what? V dot equates to 6. My head's in the way there. Equates to dot 4. Dot equates to 4. Yeah, n dot equates to 4, and j dot equates to 0. Okay? And then our trace tags here. Now, the fact that v and n are called by reference, that means that their values are addresses, and the trace tag that we use for addresses is #2h, so that the address will be displayed in hexadecimal. On the other hand, j is a local variable that has an integer value, so its trace tag is #2d. All right, and now here is the first statement in getVect, and we have to allocate storage for that j, right? So we sub sp2, and we tell the tracer that we want to label that cell with j. Okay, now here, here's where we have to input. I think this is a input, right? So we input is decim. Now, how do we get the first value into j? How do we get the first value? What addressing mode? What is j? Oh, wait. Sorry. N. My mistake. Okay, so, but the question is, what addressing mode? Well, n's just a local variable, right? And it's on the runtime stack. So what's the addressing mode? You guys know? What's he going to put down there? Oh no, wait a minute. Sorry, n is not a local variable. N is a call by reference. It's an integer that's called by reference. So what addressing mode do we use? S? No, SF. Right? Stack relative deferred. Right? I think we did an example like this before. An integer called by reference. Okay, and now we have to do the for loop, right? Okay. Load accumulator 0. Store accumulator j, stack relative, so that's the initialization. J gets 0. Now we have to do a compare. Now we do the test for the for. So we compare accumulator with n. But now what is n? SF, because it's a call by reference variable. And then branch if what? I don't have the code in front of me here, so it's hard for me to talk this through anyway. So branch if greater than or equal to blah, blah, blah. Okay? Now, the one thing we want to do is let's just see if we can get this next instruction before we close up here. Okay, so what is that next instruction? You can see it there on the slide. I don't have it memorized here, so what's coming up here is going to be a, oh yeah, we're going to do an input, right? So what are we going to input into? We're going to do a DESI eventually, but DESI using what addressing mode? Well, first thing we have to do is we load the index register with J, right? Because it's V sub J, right? The code is V sub J. So we load index J, but now what is J? It's a local variable. So what addressing mode is it? It's stack relative. And then ASLX, because there's 2 bytes per cell. And now what do we do DESI? V comma what? Sxf. And there you have it. Pretty cool, huh? Boom, boom, boom. And the rest of that you can work through yourself. And there's a get vect and a put vect. Now let's check to see if we did our code right. Okay, so there's the code. Did we do that? V, N, and J? Yeah, we did. Oh, I think, as I recall, on the board we used the accumulator for J, and on the code and the slide in the book we used the index register for J. So, but it's all the addressing modes check, right? They all verified. So you can go through that code and make sure that this is like we have it here. Branch on greater than or equal to the int4. I forget what point I was making here. Okay. So, blah, 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 blah. Play it again, Sam. Okay. And now I think we're about ready to call it quits, it looks like, because I'm clapping my hand. But, yeah. Whatever. Okay. I think we're coming up near the end with this dubbing. Sorry for the inconvenience. I apologize once again, but I think you get the picture. You can download the slides or read the book if you're still not too clear about this. And I wish I knew what I was saying, but we're about ready to wrap up, it looks like. And now I'm stalling for a little bit more time because I forgot what we were saying at the lecture because it was earlier today and I don't remember what I was talking about. And some people are asking some valuable questions that you're not going to get to hear, those of you who are listening to this, because we had this audio glitch. All right, etc., etc., etc. Ooh, it looks like I'm making an important point there. I wish I knew what it was. Oh well. I'm sure you guys will be able to figure all that stuff out. Okay? All right. Now, are we getting close to wrapping up here? Stalling for more time. I don't think there's any more info.